because if you do something which the customer really does not like or does not want, you don't get paid. So before we get into the SDLC definition, let me quickly try to identify or put before you what are the goals of SDLC. Why do we do SDLC? SDLC, as you can understand, stands for Software Development Lifecycle. It is basically a collection of processes to develop, design, maintain a software project so that we can guarantee that all functionalities along with user requirements, objectives, and final goals are met. In general, we will say that SDLC enhances a software project's quality and the developer's productivity through structured software development processes. That's taking this to be a very rudimentary introduction. And these are some of the main process stage. You gather the requirement and analyze, do the design, go on to doing the development, test what you have done, deploy to the customer and maintain. And as you do that, there may be enhancement, there may be bug fixes, so you go around this cycle. But the core point is, as a software company, what are your primary organizational objectives? Right? Certainly, the core objective is to make money by honest means through providing quality services to the customer. That's a very broad level objective. But I will point out that there are two core goals that any organization would like to meet. In fact, this is not something which is specific for software companies. Is specific for any product or service company will have that. The first objective is to be efficiency. That is, when your task is to build a system, you must build the system right. That is, you should do things right. Just as an example, if you are aware, a couple of decades back, when Windows 98 was being launched, and at then Bill Gates was at the helm of affairs at Microsoft. So there was a major launched event organized, and he just pressed the button to start Windows 98, and the system had a blue screen. It crashed. Much later, when Windows 10 was launched and subsequently used, it became one of the most popular operating systems in that space, in that office space. So certainly in terms of Windows 98, Microsoft did not do a few things right. In terms of Windows 10, they did. Right? So we'll broadly say that efficiency is the lines of quality code produced per man hour. Lines of quality code, not just any code. A code, you write 100 lines of code and that have 10 bugs, that's not a quality code. So the lines of quality codes that are produced per man hour of effort is kind of a measure of efficiency. We also call it a productivity index. And it could be the instances of quality support provided per man. There's no unique metric for this. You can also say that, well, there are support requirements which could be just queries, use clarification, or small bugs, or ways to work around things and so on. So instances of quality support you can provide per man week is another index of metric of efficiency. The bottom line is you will gain efficiency by minimizing rework. There must not be rework. You do something because it is software. You do something. Then you have to come and change that, correct that again. In the process, you may have a major loss of revenue, major loss of credibility with the customer. So you have to get it right the first time. So that's one organizational objective in essence. The other objective is called effectiveness. Right? So it's just tweaking of words, but it means a lot. Effectiveness talks about building the right system, that is, doing the right things. You may have built a great product, but if the customer does not want it, if the market does not exist for that, all of your investment in that product goes waste. So, as an example, I'll mention Iridium. I do not know if you are familiar with that project. The project Iridium was spearheaded by Motorola, Microsoft, several companies. The idea was to, put up one satellite every day in the orbit, so that from anywhere on Earth you could seamlessly call anywhere else. This project was efficiently executed. Several satellites were put up, the system worked pretty well, but the business did not happen. Why? Because the basic understanding of the user requirement was faulty. It was thought that, it will be great to be able to call anyone from the, say the desert of Sahara or from the Antarctic and so on. But as it turned out, 3/4 of the Earth is water, where except for several ships that float around, there are no human existence. There are difficult places where normal cellular phones, like in deserts, particularly, or in deep jungles of Amazon, you have not been able to put the normal cellular service there too. Iridium kind of seamless satellite phone service did not have enough takers. So Iridium was a project which was done right. It was excellently executed, but it was not the right system to build. It was not effective. It could not, all effort went bankrupt and so on. In contrast, if you look at Tesla, the electric car, which also had a lot of doubts when it was launched about a decade or little more than a decade back, was the right system. Even though at that time, the perceived need of electric vehicle was not that high, but the analysis of what should go into that product, what kind of features should be there was done well. So it was a right project to do. It's the right thing to do. Of course, it was done right as well. Right? So this is the effectiveness. So we will broadly say that lines of quality code produced per dollar is kind of one per dollar, or per currency, per rupees, whatever, or cost of every instance of support. These are measures of effectiveness. Again, the core line is you have to get it right the first time. Minimize rework is a loss. So that has to be minimized to achieve these organizational objectives. How do you do that? How do you get there? To get there, you need processes, experience of what has been done before. Based on that, defining what should be done by whom at which stage, and what are the checks and balances for that. Project monitoring and control, PMC, basically drives these processes. And if you recall my first discussion about why software is still in development, not a construction, the main gap is the ability to define proper processes and somewhat of an aversion of the human cells to follow processes strictly to achieve efficiency and effectiveness. So while we talk about SDLC, or for that matter, software engineering in general, we'll always have to keep this in mind, that the efficiency and effectiveness have to be ensured. We have to provide quality product. We have to be productive, not make many mistakes, and do everything right and do the right things. So SDLC is primarily about process compliance. In specificity, it has three objectives. You have to ensure that a high quality systems are delivered. Here, by quality, I mean, one point you'll have to remember is we often think that if something is more expensive, it has a better quality. No, that's not the meaning of quality. That's the meaning of great. That's the meaning of great. So, a seat in the economy class of travel in airlines is less expensive than the seat in the business class, which is less expensive than the seat in a first class. Does not necessarily mean that business class has better quality than the economy class, or first class has a better quality than business class. These are different grades. Quality talks about the compliance to commitment, compliance to contract. Whatever you have promised to provide to the customer, as closely as you can provide them and exceed in the process, if possible, means you have a high quality. If you compare between, say, Microsoft Word and, say, Notepad, you will obviously say that Notepad is, far more superior. It has a better grade, no doubt. Yeah, I'm sorry. Microsoft Word has a better grade. Notepad does not have that grade. But in terms of quality, you possibly cannot say that, because we all have experienced several issues with Microsoft Word while you're using it, which promises you a sea of features, and quite a few of them creates problems a number of times. Whereas Notepad has a limited set of features, but its failure rate is very, very small. So it has a lower grade, but has a better quality. Right? So that commitment to quality is the first objective. Second, SDLC must provide strong management control. You have the management in the company so that you can achieve the organizational objectives. You can ensure efficiency, effectiveness, compliance to processes. You can control cost. You can make sure that the customer is satisfied with what you're doing and all that. That will not happen just with individual effort. The management of the company, which also is a structured human process, has to have specific control on each of these aspects and more. Naturally, the CEO cannot look into every details. So you have CXOs. CXOs cannot look into every detail. So you have directors. Directors cannot look into every detail. So you have managers. Managers cannot look into every detail. So you have project leads and so on. So there's a human hierarchy of management and several processes which ensure that you have control eventually, in a good company, eventually to the contribution or the work being done by each and every developer, almost on a daily or weekly basis. Right. So strong management control is what SDLC tries to ensure, that it will define processes which can be complied with management control, can be measured. I mean, you cannot control anything which you cannot measure. Right? You know that. So the the adherence to PMC, project management and control, is a very important factor of SDLC. The third, and in many ways, the most important factor is to maximize the productivity of the system staff. Right? Why are we learning about all this object orientation, all this template meta programming, all that? To improve the quality of code that you can produce and to improve your own productivity, so that you should be able to write less and achieve more. You should be able to write correct code in the first attempt. So if you can do that, naturally, you'll be a lot more productive than if you did not have the choice of doing that as in C. So in C, you have to do a string reverse. You have to start by implementing a stack. In C++, no need. You already have it. So it just turns out to be a 5 lines of code. And the comparative effort to get a equally functional program between these two paradigms of C and C++ with templates and all that could be 1:10 or 1:50, right? So maximizing productivity is the third primary objective of SDLC. You have to keep these goals and objectives in mind to be able to understand why the processes are there and what should be there. So better quality and lower cost is the mantra that SDLC is always trying to guarantee, trying to ensure. Okay, so what are the benefits it offers? I mean, if you can comply with SDLC, it offers a lot of benefits like address the goals and problems so that the project is implemented successfully. Project members cannot proceed ahead before completion and approval of the prior stage. Remember, management control. Okay? So you cannot just keep on doing things and then you do something, your friend one goes in a different track, friend two goes in a different track, and after 1 month, you find that the code is not integrable. Such kind of things cannot happen if you follow SDLC properly. It has necessary checks at every stage so that those checks can be tested, even measured at times before you go into the final installation stage. The complications are minimized. Optimal control with minimum problems is the primary benefit of following SDLC. Okay. Having said those, setting the stage with those initial words, let me introduce you to the SDLC stages. These stages, are not sacrosanct. I should not say that they are like, absolute truth. But these stages have evolved over, several 5-6 decades of experience of millions of projects that probably billions of people have implemented, tried to implement. So these are some of the main stage activities, and how we do them is a basic question. So let me specifically go through each and every of these 5 stages with the main stages. You look at different literature, you will find, different subdivisions and all that, but broadly these 5 stages are agreed upon by the community in general. So the first is, of course, requirement gathering. You have to know what you have to build. Otherwise, you will build an iridium, right? Even if you do things right. So there has to be, how do you know that? Naturally, the customer for which you are building the project may not be as savvy about software development, software engineering, even about his or her own requirement. The customer may not be so aware. So there has to be constant communication between stakeholders. Stakeholder means whoever has something in that project. It could be customer. It could be developer. It could be the designer. It could be, say, your installation engineer. It could be the group of people who provide support over phone and so on. So everybody is a stakeholder. Whoever has something to do with that project is a stakeholder. And specifically, we would highlight the end users, whoever uses that. The end users may or may not be customers, and the project teams. Now, the requirements have to be gathered from the customer in 2 forms. One is functional, other is non-functional. Now, what is the difference between functional and a non-functional? Functional requirement is what should the software do, right? You have, let's talk about, we are talking about Word, Microsoft Word. So the functional requirements are that it is a text editor which has several ways of formatting, referencing. You can use variety of different fonts in that, and so on and so forth. I should be able to. change, edit, mark, track changes, store, restore, open it again. Those are functional requirements. There are non-functional requirements, which are beyond the functional. For example, have you ever thought that what is the biggest size of document that a Microsoft Word can handle? Right? Nothing is free in this universe. So there has to be a limit to that. If, as the document size keeps on growing, certainly, if you have dealt with the big documents in Word, you'll see slowly the performance of the Word editor is becoming bad. Now, does it become bad, subtly, unusable subtly at one point, or this degradation is graceful? If for some reason your system crashes in the middle, is there a way to restore the work that you had done? These are different kinds of non-functional requirements. Non-functional requirements could go even up to the resources that it uses. In a mobile phone application, non-functional requirements will often talk about the energy requirement of the software, the amount of heating that it does, and so on and so forth. So functional and non-functional, both kinds of requirements must be captured. And then it has to be analyzed. And how do you do that? If you expect the customer will write down the specification and give you, like I did for your assignment 3, it will be a very, very wrong assumption. Customer is God. That's the, again, a basic mantra of the industry that you must get in yourself very much. The customer is God because customer pays. But the customer has an idea about what the customer needs, but often does not know the details. So the customer does not even, customer is from his own domain. Say the customer is wants you to build a stock trading system. The customer is a trader for last 20 years. The customer thinks that, well, everybody, trading is like, you sleep, drink, breathe trading for them. So the customer will think that, well, developers will know everything. Everybody will know everything. But that's not the truth. So if the customer gives you a requirement, the requirements will often be broken, incomplete, inconsistent, and so on. And you have to, regularly interact with the customer, do interviews, do surveys to get out actually what requirements are. And then it is not enough just to get out those. You have to put them down, all these requirements, into a specification document, often called the SRS. You may, in the process, create project prototype also, just to give some idea to the customer as to what kind of system you have understood that the customer is asking for. So this obviously involves, on one side, interacting with the customer, getting to know what is required to be done. At the same time, analyzing from your perspective as to how do you go through that, how do you perceive it can be done, and so on. So requirements gathering and analysis often go hand in hand. In some texts, you'll find that they're separated out. In some, they are put together. I prefer to deal it together because analysis often gives you a lot of inputs in terms of what you should ask the customer, get clarified from the customer. Similarly, requirements often further refinement of requirements will often lead to better analysis of your system and so on. So that is stage one. The second stage is design. You have got the requirements, let's say in the form of a SRS document. So kind of, the presentation document I gave you for assignment 3 is kind of a rudimentary SRS document. SRS documents does not necessarily have a given structure and format. There are some standards specified, but often people choose to put the SRS in a form which is best suited for the kind of requirements that you have. Now, based on this, the second stage of SDLC, which is design, involves a few very basic things. First, you have to be able to perceive an architecture for your problem. What is the architecture? What will be the components? How will you organize the components? How the components will interact between them? What will happen within that framework if something does not work in the right way, and so on and so forth. Often you need to separate out requirements which are hardware and software system requirements. Like if you want to run a say an ML algorithm on a data set which has 1 trillion records, and you hope that your 32 GB laptop would be able to do that, you do not have a match. Right? So given the requirements, you have to identify what are the hardware and software systems that you should design for. What are the functional and non-functional requirements that are there? This will have to be extracted from the SRS and refined. It is quite possible that from design itself, you again go back to the analysis phase and again back to the customer survey. In trying to do the design based on what you need, we find gaps. And these gaps have to be clarified. So the system architecture. Now, often, so this basically means that from an SRS document, which is pretty much an English description, that is natural language, not English is not the right word because it could be in any other language, but which is a natural language description primarily. You have to slowly come to a model which does not have the problems of the natural language. Natural language is very powerful, but it is primarily emotional. It does not have the precision of expression. The same thing written in different, in different contexts mean different things. It is often ambiguous. It is meant to be ambiguous and therefore not good as a right design vehicle for software projects. So what you do is you try to, all the concepts that you have got from the SRS document. For example, you got the concept of fraction. As a part of SRS, you got to know that, well, fraction has certain properties, fraction has certain operations, and so on. Now, those are kind of described in a mix of English language and mathematical formulas. The question is, from that, can you create a unique, unambiguous model of the entire thing? Doing it in generality is a big challenge. And over decades, what has emerged is a modeling language called Unified Modeling Language, UML, which is kind of a graphical language. I mean, it does have, expressions, formula, all that, but it's primarily a graphical language. The reason this has settled towards a graphical language is the graphical language is universal. If you base it on any specific language, then you have, interpretation problem between different individuals. Natural language, as we explained, does not work. Not everything can be mathematically expressed in a simple way. Mathematics obviously can model everything, but if you try to do that, simple things can get unnecessarily complicated. So what people have come down to is looking at different aspects of the requirement to create different diagrams. And those collection of diagrams is called the Unified Modeling Language. We'll see this, a little later. I mean, not today, but in a couple of days, we'll see what broadly UML looks like. And then you create what is known as a high-level design. A high-level design is kind of, again, if you refer back to assignment 3, I did not present the UML of classes and all because they were very simple. But what I have provided you is a high-level design. So these are the interfaces. An interface is a high-level design, which says, okay, this is what I can, this is the behavior of this component that I want. This is the exception criteria that I want. This is the type of parameters that I want, and so on and so forth. But you do not, in a high-level design, often do not get into the details of the algorithms and data structures and implementations and all that. Those form the part of the low-level design. So broadly, you can say that designing the interface is one example of a high-level design. It could be much higher than that as well. But designing the fraction class interface or say int class interface is a high-level design. And identifying the algorithms that you need to do for each one of the interface method is a part of the low-level design. As to you identify, okay, if I have to add two fractions, this is the algorithm that I'll have to follow. So you identify that you have to have a way to find a LCM. For that, you need to find a GCD, so on and so forth, divide, all this. So that is the design phase, which is a very, very critical phase, because if you get the design wrong, everything that you do downstream is going to get wrong. Okay. Then comes the development. Development is happens to be the most time-taking stage of SDLC, where the codes are written and the system is developed and built. The actual code is written. This is what you're doing in assignment 3 and crying all the time that you do not have enough time. So the demonstration of accomplished work presented before a business analyst for further modification of work. This part is very important. It is not enough, because once you are in the development, then slowly your system is coming up. So you have components which can be demonstrated to somewhat learned audience. It may not be demonstratable to your customer because the customer does not understand your language. But there are people like business analysts who are kind of a bridge between customer who just has the requirement and you, the developers who just have the skills. So business analyst is somewhere in between, a group of people who understand the domain where the product has to be built, and at the same time understands the broad perspectives of what you are building. So whatever components you made, you may want to present it before the analyst, give a demo, maybe trial runs, and get feedback for modification right here. Because if you do not do this, then at a later stage, when a lot of things have been done, you'll be really into difficulty of making the changes. In addition to that, you will often also perform as a part of the development itself. We will discuss more on this. As a part of the development itself, we will often do unit testing. Right? Unit testing is, we mentioned about pass-fail test. Those are units. That is, what is a unit test for fraction? One unit test is, you want to see, given the right pair of numbers, is the fraction properly constructed? That's a unit. You have to have a fraction. Given two fractions which are valid, are you being able to add them and get the correct result? These are every unit. Right? So unit testing often is integrated into the development phase itself, because you need a feedback on the unit test very early. For example, if your add operator is not correctly implemented and you have not done that unit test, then it's very likely that your subtract operator will also fail. It might fail many other. Your plus assigned operator will fail. Your minus assigned operator will fail, and so on. Right? So unit testing is very important, and it's kind of integrated in this development. Next, stage 4 is testing, which is very, almost all stages of SDLC involves the testing strategy. Right? Testing is just not that you have built a system and that has a way to give input and check the output, and you make 10, 20, 100 testers sit there and keep on testing. No. Testing is a practice. Testing is a culture. You have to test everything that you do at every stage. Right? For some of it you do. For example, when you write, you are writing, say, on, suppose you are writing on Atal Bihari Vajpayee, on his life. If you write a paragraph, you will test for spelling errors, you will test for grammatical errors, you will test for correctness of expression, all of that. You keep on doing that always. So testing is something that goes into every stage of SDLC in its proper form. But the stage 4 of testing is a formal activity where it refers to checking, reporting, and fixing the system for any bug or any defect. So as you have the design of the system, you have designed how do you build the system, starting from the input requirement specification as input, starting with maybe modeling UML or mathematical models, and then HDL, high-level design, HLD, LLD, and so on. Similarly, testing involves developing a test plan. What is a test plan? In a test plan, you identify what all the system that you are building, for that, what all needs to be tested. That could be at the unit level. That could be at a mixed level. That is, you take multiple units, you have tested every operation of the fraction. Then you write a complex formula with fractions and you test whether that's a mixed kind of test. There could be directed tests. You want to specifically check that does my system properly throw exception if I'm trying to divide by 0. You may want to check for capacity. Does my system give me indication of the overflow of the numbers that are happening? Ariane rocket, you don't, I don't know if you remember Ariane rocket. It happened a couple of decades back again. It is a very prestigious rocket which crashed within a couple of seconds of its fire. It just went down. Instead of going up, it just went down. And when finally it was, the whole problem was debugged and detected, it was found that the Intel's processors, arithmetic adder module had an overflow error, which was not checked. So something which was supposed to be positive became negative, and rest is history. So testing is a very important part, where at this stage you test the system as a whole, you perform different types of tests and perform fixing of all these different bugs and defects that arise from them. The 5th stage is deployment. So you have got the requirements analyzed, designed, developed, tested. Now you feel that it is all ready. It is all ready for the customer. It is ready to be launched, as we say. So it may be released. I mean, usually you don't give the entire thing to the customer in one. Maybe you first give it to a limited set of users for testing in the real environment where it has to be used. Then if that succeeds, then you have grow your set of people who are using that. They are not testers, they are your actual customers. using the system in the actual environment, not in your laboratory, not in your laptop, not in your company's network, but in their own. Because only if those tests are successful, then you get a UAT. It's called user acceptance testing. That is, the user is finally accepted that the solution that you have given to the user is satisfactory. So this phase will involve that the system is ready for delivery, it is installed and used, errors are rectified that might have been previously missed. It will be very expensive if you have missed those. You may enhance that system inside a data center, so on and so forth. So that is how you put to deployment, and then immediately the maintenance phase start, because subsequently if there are problems reported, you have to go and fix that. Hopefully, if there are small problems, if there are bigger problems, you may have to trace back multiple stages, at times even back to the requirement stage, to fix a problem, in which case your company is going to lose enormous amount of money. You can see many of that happening in many of the projects. Several car companies had to recall car models because of faulty battery, which was igniting the cars when it should not. So this is the importance of the deployment and maintenance phase. So requirement specification and analysis, design, development, testing, deployment and maintenance. These five are the five main stages of SDLC. Let me stop a little and see if you have questions. Then I'll continue. If you have any question on the basic notion of SDLC and the stages, please ask.
So, sir, is the SRS document revised when the project goes on through the later stages?
It might. If you it might, because of multiple reasons. One, it can happen that at a certain stage in the development, say at the design phase, or even in the development phase, or even in the testing phase, you might discover that there is some inconsistency in the requirement. So those inconsistencies have to be straightened out, and that might impact again all of your design development. So on. It can also happen because suppose you are designing and implementing a system which you have not done before. So as you keep on doing that, coming to the development and testing phase, you realize that the scale at which the system was thought to be doable is not. That scale is not attainable. So you have to go back and change the specification. So it can any of this stage, from any of these stages, you may have to go back to the previous stage, previous stage, and so on. But the later this kind of things happen, certainly the penalty becomes much higher, because you can figure out that the rework will be much higher. And it's not only the rework, there could be other penalties, like you may have had a committed date of delivery. If you miss that, you get penalty in terms of payments, the payment terms. The SLA agreements might fail. SLA is service level agreement, as to what you have agreed that you will provide in terms of say the non-functional features, or in terms of the timeline, and so on and so forth. So changes are always maybe required. Our objective is to frame and follow SDLC in a way so that this change requirements can be minimized. Once you have crossed a stage, you should not require to get back to it and make changes in a later point of time. How to minimize that? So that you can minimize the rework. Okay.
Okay, sir, understood.
Okay, so let's continue. Let's say, so having seen the different stages, this is just for fun. This is a kind of comical way to say the why software projects fail, and you can see the annotations below what the customer explained and what the project leader understood and what the analyst got and so on and so forth. Now, SDLC is not a unique process. The stages that we have identified are activities that will have to be done. But how you do that, in which, I should not say order, but in which granularity you do them, and how often you revisit an earlier stage, all these are driven by different models of development that have evolved. To be more correct, is continuously evolving and will continue to evolve till software engineering, software development matures to software construction level of processes. So there are several models that exist to do SDLC. We will discuss 7 important ones, and kind of they are evolutionary over a period of decades: waterfall, iterative, V-shape, V-model, RAD, spiral, agile, and test-driven development. Just to give you a very broad idea, like in the 50s, kind of when serious mass-scale software development started with the advent of IBMs and Fortran and all that. It used to be code and fix, simply to code fix. Naturally, projects were also small. Understanding was limited. In 60s came design, code, test, maintain kind of idea. That it's not enough to code, you must have a design before that. It's not good to fix whenever you have a problem. There should be an organized way to test and maintain. So 60s. 70s saw the first formal SDLC model, the waterfall model, which is still in use, possibly the most widely used. 80s had refinements on that in terms of spiral model and so on. 90s had saw a lot of explorations into different models, RAD, V, test-driven development, and so on. And in the current millennium, the main emphasis is on agile models, right? So that's kind of the historical timeline. They are not very rigid, not very uniquely identifiable also, because many of the later models have been tried out in earlier decades. Maybe people tried, did not succeed, so people thought it's a bad idea. Then much later on, people came back to that model again and did it the correct way. So if I put the popular SDLC models in perspective, this is kind of how it will look like. So on the x-axis, as you move from left to right, you are going from formal to informal, more formal to less formal. And on the y-axis, as you go up, you are going from a sequential model to an evolutionary model, adaptive model. And you can see how are the different SDLC models placed. Right? We will revisit this diagram after we have discussed majority of these models, so that you can appreciate it much better. But the whole idea is to show that you could be very formal, very sequential, and be in this space. And for several reasons, that does not work. You can be somewhat format, but more evolutionary. That has a better success. Or it could be today, where you do Scrum, you do extreme programming, you do Kanban. Kanban, basically, it's a Japanese word. It means signboard, billboard. So you do the SDLC on the billboard, kind of. Now, talking about the models, most widely used model is STLs, is waterfall. And this diagram will tell you why is it waterfall. I mean, as the water falls along a stairway, kind of. So you do these phases one after the other. You have requirement, then you have analysis, then you have design, then you have coding, then you have software product here, which means testing and deployment. So as many, it's a linear model without any feedback. You just keep on doing things one after another. So if we try to put in perspective, then what are the strengths of this model? It is easy to understand. Achievements are well defined because you finish one phase and then go on to the next. It defines the requirements stability. It often works well when the project quality is important, because I mean, you are not mixing up phases. So you, in one phase, you do and attend the best and then you go to the next. But it has several weaknesses. The most important weakness is it cannot match the reality well. The customer cannot wait for a waterfall to end. In a waterfall model, you cannot make changes because it is happening one after the other. So while you are at a coding stage, if you want to make some changes in the specification, you'll have to trace back to the waterfall and start again. The software can be delivered only at the end of the project, because till the project ends, there is nothing in your hand. So the question is, how do you get intermediate payments? How do you raise invoices? These are practical issues with your management. Okay? It's a 2-year development cycle. So will the customer blindly keep on paying you for 2 years, or he will keep on investing for 2 years without expecting any revenue out of this? It doesn't work. Right? The business scenarios do not work with waterfall. And testing can begin only after the development phase is complete. So if you have made mistakes in your analysis, made mistakes in your design, you may be at a disaster site. Most important factor, where do you engage with the customer? You engage at the beginning when you took requirements, and you engage at the end of the project when your system is ready. Only at these 2 points. In between, if you have done things wrong, there's no way you can figure out, because the customer was not there in the room. So it's a right recipe to build a wrong system. You may have developed a high quality system, but that may not be the system that the customer wants. So waterfall often suffers from that. It works well when software projects that are already stable and you are making small changes, when the requirements do not change that frequently, when maybe the designers are knowledgeable enough that they'll be able to fully predict the problems, or the project itself is small, like the assignment tree. So under such circumstances, the waterfall model will work. It is still widely used. Naturally, in academic environments, we always follow the waterfall because we are doing small projects. We are doing projects with complete knowledge of the customer as well as the developer. And most importantly, we do not have the stick of failed revenues. We have some bit of grade, either B or C. Doesn't matter much. Now, the basic problem of waterfall is fail-led life cycle. If you look at this different stages and see, this is time, x-axis is time, y-axis is the impact of risk being tackled. Naturally, at initially it is low, because any error here, any changes here can be handled with not so much of cost. As you go into the design, the cost becomes higher because they have to come back to the analysis again. In the implementation, it's even higher. When you integrate, it goes even higher and so on. So the basic problem of the waterfall is, but you have the ability to actually test and validate with the customer only at the end. So you have a high potential risk impact for the waterfall model. So it does not allow you to fail early in the life cycle. You need to fail early in the life cycle to correct yourself. You cannot fail so late. So a bug found in early stages is cheaper in money, effort, and time. To fix the same bug found later in the process, just think about the Ariane rocket model incident I was talking of. If Intel could have found this bug, which I'm sure they could have found in an overflow in the adder at the design stage, at the implementation stage, or even at the rollout stage of the chip, it would have been much cheaper than building an Ariane rocket based on it and then trying to fly it up. So often it's said that an early defect that is left undetected until development or maintenance is estimated to be 50 to 200 times more expensive to fix. Right? So compared to if you could have fixed it in the time of requirements itself. Right? So that is about the waterfall model. I think we have run out of time. So I'll continue on the next set of models tomorrow. Meanwhile, if there are quick questions, I can take a couple. Any questions on up to what we have discussed so far? No. SDLC is not as exciting as C++, right? But we are doing all of that in C++ to satisfy that the SDLC can happen better. That's one of the primary reasons that C++ dialects are evolving from 98, 03, 11, 14, 17, 20, 23, and so on, is to ease several aspects of SDLC processes. We'll keep on touching about those as and when we come across different models. That's later. Let me close now. See you tomorrow. Have a nice day.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.